Well, Simon Tate was really quite difficult, I think. On the other hand, looking at the discussions on the forums, I think many people found it difficult because they hadn't yet made this transition to doing mathematical thinking. They were trying to do something that wasn't really required. This was very definitely the case with this one. Remember, the things I keep repeating are that one of the essences of mathematical thinking is that you first of all, you ask yourself, what is this asking me? What do I know? What does it tell me? What kind of objects is it talking about? And what do I need to do in terms of what's my target? So you have to stop, you pause, you reflect, you think about it. What you don't do, at least at the beginning, is say, does this remind me of a problem I've solved before that I can just instantly apply that previous technique? Because that can lead you in a completely the wrong direction. For example, there are various words here, and in high school, a good strategy was look for key words and try to map them into techniques. But it really isn't a good strategy in terms of advanced mathematics. Okay, there are many questions, many problems we have about perfect squares that are about the natural numbers. Okay, so what? This isn't about the natural numbers. This is about the integers. Completely different set of numbers. So, well, not a completely different set, it's a larger set of numbers. So this is about the integers. And the fact that some of the words are often used in discussions about the natural numbers, well, so be it. I mean, words get used for all sorts of contexts. Okay, so this is a question about the integers. And if it's about the integers, then why don't we just take m equals n equals 0. Then m squared plus mn plus n squared equals 0, which is 0 squared, and we are done. Folks, this is not a trick question. This is a question that gets at the heart of mathematical thinking. And the heart of mathematical thinking isn't knowing a ton of techniques from mathematics. The heart of mathematical thinking is, what do I know and what do I need to do with what I know? And what am I talking about? Stop, slow down, reflect, think. Mathematical thinking at this level is not a sprint. All of the techniques you taught were taught in high school were very good for succeeding in high school, and they certainly leave you with a lot of valuable skills. But we've been there, done that. If we're beyond the high school, if we've mastered that, then we're trying to do something else. High school sort of teaches you how to lay bricks. What we're doing now is saying, how can I take all of those bricks, which are valuable things to have, and use them to build a house? We're now going from being bricklayers to architects. We certainly need all of those bricks. I am definitely not knocking high school, right? We use the stuff all the time, but that was providing us with the basic tools. Now we're learning how to make use of those tools. Okay, that's what mathematical thinking is about. And sometimes we need a lot of tools, and sometimes we can get by with something very simple because we just ask ourselves, what am I trying to do now? And we're not getting seduced into thinking that this is just another variant of something we've met before. Think of every problem as a new problem. Then you'll find that things get much more doable, because you'll be focusing on thinking, not applying techniques. Okay, that's the end of my sermon. Well, it's not really the end of my sermon because that's what the whole course is about. But let me just move on now to question 2. And in this case, you probably haven't seen anything quite like this before. So you have to start by asking yourself, how could it happen that the answer B was a perfect square? I mean, just how could that come about? What kind of thing must happen? Well, let's just write it this way. How can we have mn plus 1 equal to p squared for some p? Well, at this point, one of those bricks that I was taught in high school becomes really useful. Because if mn plus 1 equals p squared, that means mn equals p squared minus 1. And one of the bricks I had drilled into me in high school was that p squared minus 1 is p minus 1 p plus 1. So what we're about to do is take something that was drilled into us in high school and make clever use of it, okay? Because if mn is p minus 1 p plus 1, then we could have m equals p minus 1 and n equals p plus 1. In that case, p would be m plus 1. Remember, m is the number we're given. We're trying to find an n. And I'm just using this to say, what could that n be? What must that n look like? So given an m, we'd be able to take p equals m plus 1, and then from this one, n equals p plus 2. And now we found the n. That is n plus 2. Whoops, n plus 2. Okay? P plus 1. P is n plus 1, and n is p plus 1. So n is n plus 1. So given the m, we've already found the n. So given n, let's just summarize it now. Given m, take n equals n plus 2. Then mn plus 1 equals m plus 2 plus 1, which is m squared plus 2m plus 1, which is m plus 1 squared. So we've answered the question. We've said that given an m, take n equals m plus 2, then mn plus 1 is m plus 1 squared, which is a perfect square. Now, if I hadn't gone through this, it would have appeared that this was a rabbit out of a hat trick. And unfortunately, it's a consequence of the way that mathematicians often write their papers, that they don't include all of the reasoning, they just give you the conclusions. Now this would be a relatively simple example, but if I had simply said, given m, why don't we take n equals m plus 2, you would have said, how on earth did he come up with that? What made him think of that? You know, and I look as though I've got some kind of magical ability. No, I don't. I just went in and said, well, how could I possibly get to that answer? And then it was just something I learned in high school. Okay? So, you know, one of the techniques is just say, how could I possibly get the answer that I'm asked to find? Now, I'm couching this in terms of classroom questions, but the same issue arises when you're dealing with mathematical problems in the real world. Look at the problem. What does it tell you? What do you have to do? How can I get the answer that I'm going for? So this might be a simple classroomy type example, but it has many of the elements of good mathematical thinking. And in this case, it was, how can that answer possibly arise? And as soon as I sort of start to look at that, it just drops out. Okay? Recognizing that was the entire key to the thing. Once you've done that, straightforward. Okay, let's move on and look at the next one, question 3. Well, question 2 is another one of these things that when you first meet it, you think, wow, this is asking me for something really deep. How could I possibly come up with a quadratic, all of whose values are composite? How could I guarantee that all of the values are composite? Sounds as though it's going to be really deep, but no, if you sort of just take a breath, sit back and say, you know, how could it happen that numbers are composite? Well, if they're composite, they have to be the product of two other numbers. Okay, wait a minute. Why don't we just take, if that's going to always be the product of two whole numbers, let's make it the product of two whole numbers. And lo and behold, that is indeed of the form n squared plus bn plus c, where b and c are positive. That's all there is to it. We just wrote one down instantly. We didn't have to prove that one exists. We did prove it, but we did it by just writing one down. And all we had to say to ourselves is, no, this sounds complicated, but no, all it means is that the values are products. And quadratics are products of things. So we just write it. We explicitly make it a product of two things. The value will always be the product of two numbers, n plus 1 and n plus 2. And it's for all positive integers. So we'll have maybe 2 and 3 or whatever. So these are always greater than 1. So this thing is composite. N squared plus 3n plus 2 is always composite. That's it. Didn't involve any advanced machinery. Just thinking about what the problem asks us to do. Very similar with this one. You know, it sounds deep. Oh, it's about the Goldbach conjecture, a problem that's been around for hundreds of years, hasn't been solved. How on earth can we do anything with the Goldbach conjecture? Well, the answer is just look at what it tells us and ask us what we can do with it. And first of all, we observe that this is talking about numbers n bigger than 5 that are odd. Well, if n is an odd number bigger than 5, then n is of the form 2k plus 3, where k is bigger than 1. I mean, normally we think of odd numbers as being of the form 2k plus 1. But because I'm looking for prime numbers here, I'm going to write it as 2k plus 3. And I can do that because n is bigger than 5. So for numbers bigger than 5, any odd number bigger than 5 is of the form 2k plus 3 where k is bigger than 1. Well, in that case, since 2k is bigger than 2, because k is bigger than 1, 2k is an even number bigger than 2. So by Goldbach's conjecture, 2k equals p plus q, where p and q are primes. In which case, n, which is 2k plus 3, is p plus q plus 3. The sum of 3 primes. We're done. Actually, it wasn't difficult at all. Once we sort of thought about what it says, all of the complexity is in this unsolved problem, Goldbach's conjecture. If we assume Goldbach's conjecture, which we're allowed to because it says if that's true, then every even number bigger than 5 is the sum of 3 primes. One of which, in the case of our proof, is 3. That was it. Okay. Actually, it wasn't difficult at all. It just looked as though it might be when we first met it. So another lesson we can learn is don't get put off because something looks complicated. Until you think about it, you don't really know whether it's complicated or not. Okay. A couple more on this assignment sheet, and then we're done with it. Well, questions 5 and question 6, the last two questions, they're both induction proofs. So what I'm going to do is I'm going to do example 5, and then I'll leave you to do number 6. If you've already tried it and failed and you came here looking for an answer, you're not going to find it explicitly, but hopefully by watching me go through another example, namely number 5, you'll be able to go back and do number 6. Because these things are all very similar, at least the ones I'm giving you are all very similar. Not all induction proofs are similar, but these, the ones I'm giving you from number theory are all very similar. Okay. Well, the first thing you have to do is express this as for some kind of an equation, with a formula in it, because otherwise we're going to deal with this expression as sum of the first n odd numbers. So we're going to have to write down a formula for the sum of the first n odd numbers. So what it asks us to do is show that 1 plus 3 plus 5 plus, and then the nth one is 2n minus 1. And we have to show that equals n squared. Okay. Arguably the hardest part of this whole thing is figuring out what the last term is. Okay, so that's what we have to prove, and we're going to do it by induction. We're told to use by induction, so we have to begin by looking at the first case. For n equals 1, this becomes just 1 equals 1 squared, which is true. So it's true for n equals 1. Okay, so now let's assume the result. Let me call that star. So let me now assume star. And now I need to prove the corresponding result with an n plus 1 in place of n. So why don't I just add the next term to both sides? The next term would be 2n plus 1 to both sides of star, in which case I get 1 plus 3 plus 5 plus 2n minus 1 plus 2n plus 1. This is the first n plus 1. Okay, that's the first n plus 1 odd numbers. This is the next case in the induction. And now when I add 2n plus 1 to the right hand side, it becomes that. Wait a minute, I can now use another of those bricks that I learnt in high school. Thank you to my high school math teachers, because now I can just get this one straight out. This was drilled into me. Boy, it's good to have these things at my fingertips. That's n plus 1 squared. We're done. It's the same formula with n plus 1 in place of n. Wasn't difficult at all. In fact, all of the machinery I needed to solve this one, I learnt in high school. The one thing I didn't learn in high school, at least not very well, was how to strategize about a novel problem. And that's what this course is about. This is how do you take all of that great stuff you learned in high school and strategize and use it and get new results and think about new problems. But before you do that, you have to ask yourself, what is the problem I'm given? what do I know about it, and what am I having to prove? And if you misread a sentence, you're going to end up doing the wrong problem. There were a lot of people writing on the forums where what they were really saying was, I demonstrated all my high school skills and great virtuosity and solved a problem that I wasn't asked to solve. Well, in this course, there's very little penalty for doing that, except you feel bad. If this wasn't a course, if you were working for a large corporation, you might be out of a job or demoted or moved to a less interesting job. So this is a low penalty experience for how to think mathematically, and which is why these MOOCs are great. Okay, well, as I say, I'm going to leave you to do question 6, and having seen another example, I hope you're not put off by the formulas and the complexity in question 6. It's really just logical thinking, okay, mathematical thinking. Okay, so much for assignment 8. Seemed hard at the time, actually was hard, but hopefully it doesn't seem quite so hard now. It's not hard if you become a good mathematical thinker, and that's achieving that is what the whole thing's about. Okay.